Welcome to the third part of Lecture 1. In the previous lecture, we learned about complex numbers. We learned complex numbers can be equipped with addition, just taking the sum of numbers. We learned this forms a group. We also learned if you think about R2 and the component-wise addition of pairs, it is also a group. And we learned these two groups are essentially the same thing, right? Now, we want to go one step further. We want to learn about another algebraic structure on C. So when we have two complex numbers, we can also think about their multiplication. So for instance, when we have two real numbers, 2 and 3, we can say what is 2 times 3, right? We want to do the same for complex numbers. We want to say if you have a complex number Z1 and another complex number Z2, what is Z1 times Z2? So the point is that we should define this. For us, the set of complex numbers is a new set. So we should say how we are going to define their multiplication, right? So if Z1 and Z2 are two complex numbers, we learned each of them can be written as following. So Z1 can be written as x1 plus I y1. Z2 can be written as x2 plus I y2. Right. What is Z1 times Z2? So in order to define this, we want to respect some essential algebraic properties of multiplication. So the definition of Z1, Z2 is given so that the associativity, distribution, etc. would still hold. So we have x1 plus I y1 times x2 plus I y2. We define the product so that the following would hold. We would have x1 times x2, and then we would have x1 times y2 times I. However, the order doesn't matter. Everything is commutative. So this is how we define it. So it would be I, x1, y2. And then the next step would be considering I, y1, x2. So we have I, y1, x2 plus, and then we have I, y1, I, y2, but I squared is minus 1. So we get negative y1, y2. Okay, so what is the result? We have a real part, which is x1, x2 minus y1, y2, and we have an imaginary part. The imaginary part is x1, y2 plus y1, x2, right? So formally we say we define Z1 times Z2 to be x1, x2 minus y1, y2 plus I, x1, y2 plus x2, y1. This is the definition. This is how we are defining it. This notation means we define the Z1 times Z2 to be the following. But the reason we define it this way is that this is the natural way to do so. So now the set of complex numbers has addition, but also has multiplication, right? Now we have two algebraic structures on C, both addition and multiplication. The essential thing is that all the good natural algebraic axioms for addition and multiplication that we know holds for these. So for instance, if we have Z1 times Z2 plus Z3, it is equal to Z1, Z2 plus Z1, Z3. Or we have associativity with respect to product 2. If we have Z1, Z2, Z3, it doesn't matter first to consider multiplication of Z1 and Z2 and then the result by Z3, or first Z2 and Z3 and then the result by Z1. It's commutative. Z1 times Z2 is equal to Z2 times Z1. It has the identity for product. So we have 1 as a complex number. It's 1 plus 0 times I, and 1 times any complex number Z is equal to Z. So it is identity for multiplication. And the last important thing is that any complex number Z, which is not zero, is non-zero, it has an inverse. There is another complex number denoted by Z inverse, so that Z inverse times Z equals Z times Z inverse equals 1. I leave this as an exercise, but suppose Z is x plus iy, right? Z inverse would be 1 over x plus iy. We should say this is a complex number, right? But in order for this number to be a complex number, it should be some real number plus I times another real number. So we should be able to rewrite the left-hand side in the form of the right-hand side. So you should tell me what A and B are here. So this would hold. But anyways, you can do this. Now, the set of complex numbers with addition and multiplication so that it satisfies all the properties we saw, this has a name. Any algebraic structure with these properties, addition and multiplication with the properties we listed, is called a field. So C is an example of a field. R, the set of real numbers, is also a field, right? The set of integers is not a field, right? So the set of integers, this is not a field. Why is that? Because we don't have inverse with respect to multiplication. What is the inverse of 2? It's 1 over 2, but it's not an integer. But R and C are fields. So R is a subset of C. It's actually a subfield of C. So we had the field of the real numbers. Now we have a larger field, C. And this is actually, in some sense, better as a field. It has an essential property that R does not have as a field. So what do I mean by better? C is algebraically closed. What does it mean? C is algebraically closed. What does it mean? So we know in R there are polynomials like x squared plus 1 equal to 0 that they don't have any solution in R. So it has no solution in R. This does not happen in C. Any polynomial in C has a root, has a solution. So we know x squared plus 1 has one solution at least, that's I. We know it has, in fact, another second solution, right? If I squared is equal to minus 1, there is another number that if you square it, it would be equal to minus 1, and that's minus I, right? Minus I squared is equal to minus I times minus I, which is plus I squared, which is minus 1. So negative I squared is also equal to minus 1. So x squared plus 1 has two solutions in C. So this is essentially true. A polynomial with degree n has exactly n solutions in C. If you consider solutions with multiplicities. For instance, if you think about x minus 1 squared equals 0, it has only one solution, x equals to 1, but it has with multiplicity 2. So if you look at solutions with their multiplicity, any polynomial of degree n has exactly n solution in C. So algebraically closed means every polynomial has a solution in the field. R as a field is not closed. C as a field is closed. So any polynomial you write, x to the 4 plus x squared plus 5 equals 0, even if it doesn't have any solutions in R, it would have solutions in C. And counted with multiplicity, this equation would have 4 solutions. So I can write any polynomial has roots in C. This is what it means by algebraically closed. Actually, there's a small mistake in this sentence, but I leave that to you. Can you see what is the small mistake here?